Today's lesson is over molarity, molality, and dilution. We're going to talk about what these specific terms mean, how these terms help us study and understand solutions in solution chemistry, and then we're also going to practice a bunch of calculations with these concepts. So we're going to need our calculator for sure today, and probably our periodic table since this is chemistry. But let's get into what molarity, molality, and the process of dilution is. All right. Concentration. We are introducing this topic of what a concentration is or represents. The concentration of a solution is a measure of the amount of solute in a given amount of solvent. So here I have a wonderful picture representation which really helps me kind of understand this term of concentration. Over here, the little picture of the container on the right here looks like it's got a lot of solute in there. Over here on the left, it looks like there is not so much solute over here. So I kind of have a gradient that I can create of varying concentrations of solute, meaning the amount of solute that I have in a certain or a same amount of solvent. Okay? Now, concentrated versus dilute. I can represent how concentrated or the concentration of a solution by these terms. A concentrated solution has a relatively large amount of solute in a solvent. Okay, so over here on this picture, this is a concentrated solution. I have a lot of salt being dissolved into my solvent, so I have a lot of solute particles within the solution. It's concentrated. Now over here, a dilute solution has a relatively small amount of solute in a solvent. So if I were to put only a little bit of salt solute into my solvent, I would have very few particles of solute in my solution. So these terms are a great way to just kind of casually state how much solute you have in your solution. But it is all kind of relative here. And what I mean by that is, going back to my gradient, I can say, yeah, this section over here is diluted or dilute, and as I move in this direction over here, I become more and more concentrated. But these terms dilute and concentrated are only like a qualitative way to describe how much solute is dissolved. Qualitative means with words verbally describing things. Now, we know in science we need more quantitative and precise way to talk about concentration of a solution. We need maybe some numbers, some values, some measurements that give us exactly not a relative amount of solute from one to another, but exact values. We need a way to describe exactly how much solute is dissolved, okay? Molarity and molality gives us quantitative measured values of concentration. So let's get into our first one of those with molarity. The symbol for molarity is big ol' capital M. Molarity is the number of moles of solute in 1 liter of my entire solution, okay? So here's the equation that we use to not only define what molarity is, but also it's going to help us calculate how to solve for molarity. I'm going to take the amount of solute, the moles specifically of solute, and I'm going to divide that by the total volume of my entire solution, the liters of the solution, okay? Now, I like to kind of abbreviate this equation for molarity with this. Big ol' M, which is molarity, is equal to the moles over liters, with that moles thing on top being the moles of the solute part of the solution, and that liters on the bottom representing the volume of the entire solution, okay? So yeah, basically I'm dividing moles by liters, but there are some things that I can kind of throw at you to make these problems only slightly more challenging. So for some tips, if I'm giving you grams of the solute, you can actually convert grams into moles of the solute, and then you can plug it into this molarity equation and totally solve your grade. I know I can convert from grams to moles using my molar mass on my periodic table, so that is nothing too challenging for me. It's just something to be aware of, that it could be a possibility. Another thing I can maybe throw at you is, instead of giving you the liters representation of this solution, I could give you milliliters. That's probably even more common when we talk about solution chemistry, is to get it in milliliters. But y'all, that is straight metric. Going from milliliters to liters is all you have to do is divide by 1,000. Okay, so I thought that we would bounce down onto my document camera and maybe do some practice problems with some molarity, right? So we have 3 practice problems that I want us to do today. Okay, so on the practice problems, you know me, I like to really circle things that they've given me and kind of identify what that is in my reaction or in my problem so I can better implement how to put them into the equation for molarity. So here's my equation for molarity. Once again, we know that if they give me grams, I can convert to moles. Notice I did a little double-headed arrow. That's because sometimes I may use this molarity equation to ask you to solve for the grams of the solute, which then first you would solve for moles of the solute, and then you would take it to grams utilizing the conversion with my molar mass. Okay, so that was a digression, but that is a possibility, okay? So the first example, it says calculate the molarity. So I'm solving for molarity, and you guys, look how sneaky they were. They told you, by the way, if you forgot, molarity is symbol is capital N. I'm like, great, I know I'm solving for this right here. Of a solution prepared by dissolving 12 grams of potassium permanganate in enough water to make 750 milliliters of solution. So I have this 750 milliliters of solution. You guys, that's going to be eventually translated to my liters of solution that I'm gonna put on the bottom. But we do know that in order to convert from milliliters to liters, I just have to divide by 1,000, which means I'm going to move the decimal 3 places that way. So this guy right here is going to be 0.750 liters. So that's going to be on the bottom here. Now you're like, okay, if I'm solving for molarity, I know that the equation for molarity is moles of my solute over liters of my solution. I got that bottom number, but they did not give me the moles of my solute. I'm upset. Don't be too upset. They gave you grams. We mentioned that I can convert from grams to moles using the molar mass. The molar mass of who? Well, they told you potassium permanganate, and they also gave you the chemical formula. You're welcome to where I find the molar mass of all of that business down there. So I'm actually going to do that first. I'm going to have to convert to moles. So we're going to do that first. So I'm going to set up a one-step conversion factor where I do 12.0 grams. I'm going to write my formula for this so I can visually see it on the spot that I'm working at, to where I can know what all I have to grab from my periodic table in terms of my molar mass. So I already need my calculator here, you guys. Oh my gosh. So on my periodic table, it looks like I have 1 potassium in that formula. Where's the potassium? He is over here. He is an alkali metal, yes. So my first value is going to be 39.1. I have 1 potassium. The next guy that I have manganese. I have 1 manganese. Here's manganese right here. So his value is 54.94, and then I have 4 oxygens. So each one of my oxygens has a molar mass of 16. So I have to multiply all of those by 4. Okay, so what I have here is potassium's molar mass, I have manganese's molar mass, and I have the molar mass of all 4 of those oxygens. I hit enter. So that's the molar mass of potassium permanganate. We are super excited about that. Not a big deal for me. I'm going to write that down here. That represents that there's 158.04 grams in every 1 mole. Okay, so the grams cancels off, and on top and on bottom, so that way I know that the answer from this calculation, if I take 12, dividing it by that molar mass, I will get the moles of potassium permanganate, which is what you need to plug into my molarity calculation. So I'm going to say 12 divided by that answer that I previously solved for, that molar mass, and this is the number of moles. Now, if we're being super precise scientists, we don't want to just chop off this number as is. We're going to try to keep this on our calculator. I am going to write this off to the side just so I can utilize that and pull that number into my molarity calculation. But I'm going to let my calculator here hang out so I can grab that precise number when I need to eventually when I solve for molarity. Okay, so yeah, that's my value. Y'all, we are good to go. We now have my moles of my solute, which is potassium permanganate. So I have 0.0759 moles. Once again, specifying, I'm writing units every single time so I know that I'm not going to mess up. Divided by my volume of the solution is 0.750 liters, right? So now my calculator, I am ready to take that precise value of moles that I still have and divide that by 0.750, and then I get my final answer. Okay, so that is the molarity, okay? Now, to round to the certain number of sig figs, I have to look at all the numbers in the problem. This number has 3 sig figs. This number has 3 sig figs, so I will round my final answer to 3 significant figures, which would be 0.101 m. The unit and the symbol for molarity is a capital M. So I would say that if I were to prepare this solution, it is a 0.101 molar solution of potassium permanganate. That is a much more precise way for me to express, well, how much potassium permanganate do I have in that aqueous solution than just me saying, well, it's a dilute solution of potassium permanganate. I'm giving you actual quantitative values. Okay, so that one was a little fun because we got to deal with some of the mass business, pulling it in to make it to moles and then solving for molarity. All right, let's do a couple of more problems. Example number 2 says calculate the moles of sodium chloride. So I'm solving for moles. Oh my gosh, I'm actually going to be solving for this top number here, which is super exciting. So how many moles are needed to prepare 175 milliliters of a 0.500 molar saline solution? So I have given you the molarity. I have given you that number right there. I have also given you the volume. Yes, it is not in liters, but that is a real quick way to bump my decimal back to go 0.175 liters. Okay, I have the 2 other things that I need to solve for moles. The only thing sneaky that I have to do is I just have to rearrange my equation, right? So rearranging this equation is a little bit sneaky. I have to multiply both sides by liters. So the liters cancel out. To where this rearranges to state, I have moles being equal to my molarity times my liters. Okay, I got both of those things. We said my molarity is 0.500 molar, and my liters is 0.175 liters. If I multiply those 2 things together, I will get my answers moles. How many moles are in that specific solution? So I go 0.5 times 0.175, and I get this. How many sig figs? It looks like all of the numbers in my problem have 3 sig figs, so my answer needs to be rounded to 3 sig figs, which means I go 0.0. Keep in mind, those decimals that lead into a number are never significant. So my first sig fig is 8, and then 7, and then 5, exactly. And the answer, or the units for this, is I used to solve for moles, so I'm really, really excited. So one certain thing to kind of look at here is that the way the molarity equation is expressed, not only the symbols in the, or I'd say the symbols in the equation setup are also going to be the units of these numerical values that I would use to represent them when I get my final answers, which is, super nice and convenient. We like that. All right, last example on molarity. It says calculate the liters. I'm solving for liters. Oh my gosh. Needed to prepare a 2.5 molar solution, or molar sodium hydroxide solution containing 31.52 moles of sodium hydroxide. So I'm solving for liters here. Okay, did they give me the other 2 things? Did they give me the molarity? Did they give me the moles? Molarity? Yep. Moles, yep, we are ready to solve for liters. I just have to rearrange my equation around to where I take this original equation, molarity is equal to moles over liters, and I got to first multiply both sides by liters. Yes? So this is kind of where we were hanging out last time. We actually used this manipulation of the equation to solve for moles last time, but I'm using this to solve for liters. So what do I have to do? What do I have to do? I got to get rid of the sneaky buddy right here. Molarity is stuck to liters. I got to get rid of him by dividing both sides by molarity. Yes? So my liters are going to be moles over molarity. Sorry, this is a little bit of a lesson in algebra. I don't know why I'm choosing today to kind of just like review going over equations. If you're interested, you can turn this equation on your own into a little triangle, kind of similar to our density triangle, to where the moles are on the top and the molarity and the liters are on the bottom. So that way you can cover up with your finger whichever value you're asking to solve for, and then whatever is remaining behind is the equation that you use. So for example, if I was asking you to solve for molarity, you cover up molarity, boom, it's moles divided by liters. If I want for you to solve for moles, like we did in the previous example, cover up moles, boom, it's molarity times liters. Here we are solving for liters, which means that when I cover it up there, I get the moles over the molarity. So if that is something useful to you, you can rock and roll with that triangle. Okay, so I'm gonna move this up. Sorry, I was getting close to the bottom of the page. So to solve my liters, I take the moles divided by the molarity. We feel good about this. So 31.52 moles on the top, and then 2.5 molar on the bottom. So if I were to divide those two things, I'm going to get the answer. Hopefully, we will see. You never know. 31.52 divided by 2.5. Okay, so that's my answer. Looking at the numbers in the problem, this guy right over here has got 4 sig figs. Woo! But this guy only has 2. So I need to round my final answer to only 2 sig figs, which means I want the 1 and I want that 2, but I have to round that 2 up to a 3 because of the 6 directly behind it. So my answer is 13 liters. Amazing. So that is molarity. Now let's talk about how, if I were an actual scientist in the lab, how would I prepare a solution of a certain desired amount of molarity? So here's an image showing how I were to prepare a solution. Specifically, this says how to prepare a 1 molar sodium chloride solution. So this would be 100 capital M. Well, we know the definition of molarity is how many moles of a solute you have in a liter of solution. So if I'm asking you to prepare a 1 molar solution, that means I want 1 mole of sodium chloride in every 1 liter of sodium chloride. So the way that you technically do this is you first pull yourself out something that's called a volumetric flask. This is this funny tear-shaped flask with like a really, really, really long neck. Now, I want you to notice about these volumetric flasks is that there's no graduations or tick marks representing a measuring of volume. That's because these volumetric flasks are strictly used for making one and only one volume, meaning up here at the top of the neck, you're going to see 1 line. And that 1 line is going to be the exact volume for whatever volume that volumetric flask is represented with. Okay, so if I'm preparing a 1 molar solution of sodium chloride, I need to put 1 mole of sodium chloride in 1 liter of solution. So I would grab a 1 liter volumetric flask where the tick mark would represent a volume of 1 liter. Okay, so now let's back it up. So I said I had to put 1 mole of sodium chloride into my volumetric flask, and 1 mole is 58.44 grams. I would calculate that from my periodic table. That is the molar mass, or the mass of every 1 mole of sodium chloride. So I add that to my flask, and then I'm going to add with my squirt bottle a little bit of distilled water, enough to where I can swirl and dissolve my solute. After I've done that, then I'm going to fill the remainder up of the volumetric flask all the way to the tick mark, mixing as I go along, stopping when I get to the line. Once I've gotten to the line, I've reached a total solution volume of 1 liter, and that would mean I would have a 1 molar solution of sodium chloride. This is a very common, very standard, very important lab technique that all scientists are used to doing all of the time, is making molar solutions of any desired concentration of a solute. So that's pretty cool. All right, so that was molarity. Molarity is a way to represent how much solute I have in a solution. This is another way to represent how much solute you have in your solution. It's molality. And I'm sorry, I do not know why they made these two terms so similar. Molality and molarity sound very similar. They also have similar symbols. Molality is now a lowercase m. So how is molality different than molarity? So molality is the number of moles of solute. Okay, so that's still the same, moles of solute, in 1 kilogram of solvent. This is where it gets different between molarity and molality. The top part of this equation is totally the same, the amount of solute in moles. Now the bottom part is different in a couple of ways. First of all, I'm taking a mass, not a volume like I was with molarity. Mass in kilograms, not a volume of liters like with molarity. Another sneaky thing that a lot of people tend to forget is it's not the mass of the solution like I had with molarity. As a reminder, the solution is 2 things coming together, both the solute and the solvent's volume that we use for molarity. Here, I want the mass of just the solute part in kilograms. So I would add a desired number of moles of solute to a certain kilograms already measured out of the solvent that I am using for my solution. Okay, I can abbreviate this in a similar fashion to the way I abbreviated my molarity equation by saying that molality is moles over kilograms, just noting that the kilograms is of strictly the solvent part. There are some sneaky things I can throw at you. I can totally give you grams instead of moles. We talked about this last time, but notice I put grams of this solute. You're like, why should I care? It's always going to be grams to moles. Well, we talked about that bottom part of this equation representing my solvent, which means Yeah, I have the ability to also give you grams of the solvent, which means you have got to be able to figure out, well, what part in this problem is the solute and which is the solvent, okay? Because you would have to calculate or convert the grams of my solute to moles using that molar mass, but I would just convert the grams of solvent to kilograms using the metric system and moving the decimal back 3 places or dividing by 1,000. Okay, so let's see what we can do here with some molality problems. I'm really excited about some molality problems. Okay, it says a solution was prepared by dissolving 17.1 grams of sucrose in 125 grams of water. Find the molal concentration of this solution. Once again, I hate that they're so similar, but if this said molar, I'd be using molarity. It says molal, which means I'm using molality. So I'm solving for molality. Yes. And give me some numbers here. Oh no, you guys. They gave me a grams here and a grams here. What am I to do? How am I supposed to assemble all my things? First of all, I'm going to write the equation for molality so we can look at this here. So molality is moles of my solute over kilograms of my solvent, right? I can turn those grams into either one of these two things, but how do I know which one is the solute and how do I know which one is the solvent that I have to manipulate? 17.1 grams of sucrose in 125 grams of water. Yes, this is an aqueous solution, so this totally is going to be my solvent, and then my sucrose is going to be my solute, which is very exciting. So my solute, I take that grams and I'm going to convert it to moles using dimensional analysis. And this one is the easier one. I just get to move the decimal place back 3 times. So I can do that right now. My solvent in kilograms is going to be 0.125 kilograms. So that's going to go on the bottom. But first, let's go tackle this sucrose business right here. So I'm going to set up a conversion. I have 17.1 grams. And my solute is sucrose. I've given you the formula here, so we got to figure out how many grams are in 1 mole of sucrose. Let's see. It's going to be a lot of math for me. That's okay. Carbon, according to my periodic table, each one of my carbon atoms has a molar mass of 12.01, and there are 12 of them, so times 12. Plus, my next element is hydrogen. Each hydrogen has a molar mass of 1.01, and there are 22 of them, times 22. And then I have oxygen. Each oxygen's molar mass is 16, and I have 11 of them, so I times by 11. So my total molar mass of sucrose is 342.34 grams in every 1 mole. Okay, so I'm going to take the 17.1 and I'm going to divide it by that molar mass, and that answer will be how many moles of sucrose I have in that solution. So I have 0.0. Once again, we're just going to give ourselves a few numbers here. We will round at the end, meaning we will keep this in our calculator to where when we solve for molality, we're good to go after that. Okay, so that's my value. So now I go, all of that is going to be equal to, here's my moles part, that goes on top, that represents the moles of my solute. I have the more precise value still in my calculator hanging around, and then I'm going to divide that by the kilograms value of my solvent. Okay, I think I know we're going to be okay. I think we're going to be okay. We'll have to see. So I take that answer, my moles, divided by 0.125. Yes? 0.3996, blah, 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 blah. So all of the numbers in my problem have 3 sig figs. I'll have to round this answer to 3 sig figs. And watch this right now. This is nutso business. Okay, so I want the 3, I want the 9, and I want that 9, but that last 6 tells me to round that 9 up to a 10, which means I got to round that next 9 up to a 10, which means that 3 gets rounded up to a 4. You're like, oh my gosh, the sig figs of it all are going to be a disaster. Well, not really. Because guess what? I can still represent that with 3 sig figs because we know that trailing zeros, if there's a decimal in the number, are significant. And the units for this molality is little m molal. So this represents how many moles of solute I have in kilograms of solvent. Okay, so now this poses the question. Molarity and molality both describe concentration, meaning how much stuff is in my solution. How can you possibly know which one to use? We kind of previewed this on our previous problem. If I give you a volume of the overall solution, you use capital M molarity. If I give you a mass of the solvent, you use little m molality. So let's see if we can tackle a problem which, if they do not outright say solve for the molarity or solve for the molality, if they just say what is the concentration, you're going to have to pick and choose what value of concentration you can solve for and express. So let's see this last little example dealing with this concept. It says, what is the concentration? So here we go. What is the concentration? So that could be M, capital M, or lowercase m, molarity or molality. We're going to have to see what they gave us to figure out what we can solve for. Containing 18.2 grams of hydrochloric acid and 250 grams of water. They gave you a mass of the solvent. Once again, this is the solvent, and the hydrochloric acid part is the solution, or solute part of the solution. I know that the solute is hydrochloric acid because the solute is less in amount, and 18.2, yes, looks like it is much less than 250 grams, okay? So what we do with these numbers, since we know I'm solving for molality now, I know the equation for molality is moles over kilograms. I've got to manipulate both of these grams measurements to figure out how to get them into this equation. The solvent, I just got to convert that to kilograms by moving the decimal. So that is 0.250 kilograms. This guy, I've got to convert it using the molar mass of hydrochloric acid, right? So I'm going to, let's put this down here. Yeah, 18.2 grams. And let's grab my periodic table. I have one hydrogen in hydrochloric acid. The hydrogen's molar mass is 1.01. And I have one chlorine in hydrochloric acid. I'm going to double check myself, but I do think that it is 35.45. I was right. I got my molar masses memorized most of the time, you guys. 35.45. So the molar mass of overall hydrochloric acid is 36.46 grams in every 1 mole. Solve for that. 18.2 divided by my answer that I already created for my molar mass. Okay, so wow. Once again, we do not have to worry about rounding just yet. So if you want to just give yourselves a few numbers just to write down and manipulate, we'll keep this in our calculator. So we have my moles of my solute. We have my kilograms of my solvent. We can now solve for molality. My moles goes on top. My kilograms goes on bottom. So I take that answer in my calculator and just divide it by 0.25. Divided by 0.25. That's my answer. So that's the molality. That's the concentration of how much stuff I have in my solution. So we're going to say that is going to be equal to, what's the sig figs? What's the sig figs? Everybody has 3 sig figs, so I'm going to round my answer to 3 sig figs. So we have it would be 9.9, but I'm going to round that. Oh, well, lots of this fun stuff right here. Everybody gets rounded up to eventually it's going to be 2.00 molal solution. So that is a way to represent the concentration of a solution, how much solute I have in that solution with molality and molarity. Now we can use these concentration understandings, or the concept of a concentration in a actual numerical value of molarity, molality, and utilize this process called dilution. Dilution is a process of decreasing the concentration, or I like to think about this as watering down of a solution, okay? Super concentrated stock solutions are frequently diluted or watered down to make solutions of any desired molarity of a lower concentration. Dilution technically means to add more solvent without changing or adding the amount of solute that is already in there, okay? And so typically in solution chemistry, well, pretty much always, our solvent is going to be water. This is why I think of dilution as watering down. To where here, if I have a solution here, and I can kind of look at the particles here of the solute that's represented in there, if I just add water to what is already in there, I'm not changing the number of red solutes in there. They're going to be still the same, okay? But they're going to spread out a lot more because I've increased the volume of the overall solution. So here I have diluted diluted this original solution just by adding water. So that's the mentality behind this. So how does this like look in terms of like, how can I figure out how to dilute something? I have this cool thing called the dilution equation. M1 times V1 is equal to M2 times V2, where M stands for molarity and V stands for volume. My ones is the solution before I've diluted it, meaning the concentrated stock solution of like the highest concentration that you're going to have in your chemical stock room. And the 2 is the solution after you have diluted it or watered it down, my new diluted solution. So molarity, we know the units for molarity are going to be a capital N. Now the units for volume, you're like, oh great, do they have to be in liters? They can. They can also be in milliliters for this because nobody cares as long as they are the same on both sides. So that's just something to keep in mind. Now, this equation is super easy. Where I find that students get tripped up as you guys are like, well, I can solve for a value, but what does this value even mean? So I like to provide a visual thing here. So if in this flask, I have a sample of my original super concentrated solution of some sort of known molarity or concentration value, and I have a certain amount of volume of that concentrated solution. So that would be my M1 and my V1, what I got starting and what I got starting for volume. Now I'm gonna water it down. I'm gonna add water until I create a different solution. It's going to be less concentrated. So it'll be a different molarity in M2. And yeah, by adding water, I've changed the volume. So you will have a new total volume, a V2, okay? So the way I think about this is you change your M's by changing the V's, meaning you add water to whatever your original V1 value is to get that total new volume of that diluted solution for your V2. Okay, so how does this actually look in the lab? So you go to any lab chemical stockroom and they're gonna have like a super concentrated solution of most solutions. Like we do a lot of work with like 1 molar hydrochloric acid or even like 0.1 molar hydrochloric acid or like 3 molar hydrochloric acid, but we are not going to hold in our stockroom hydrochloric acid solutions of every possible infinite number of dilutions that we would want. That would take up way too much space, right? What we typically have is 1 solution of hydrochloric acid and the strongest, most concentrated, and therefore the most scary one to work with. Okay, like a 12 molar hydrochloric acid solution. Well, with this process of dilution, I can take some of that 12 molar out and put it into a new container and then just water it down by adding enough water to create whatever my desired new concentration is. And this is a typical, very common lab technique that every lab scientist is used to doing and needs to do to navigate through their lab process. So let's go through a few examples before we bounce down and do them together under the document camera. I thought we would kind of implement this technique of like, what is even this process with the letter or with the words and the numbers here even asking me to do? Well, let's see. It says you want 500 milliliters of a 2 molar solution. That is what I want. This is my goal. This is the solution I want to make. 2 molar solution and I want 500 milliliters of it. And you have a 5 molar, a more concentrated 5 molar solution to start with. Well, what volume of that stock solution, that more concentrated 5 molar solution, do you need? So with these numbers in the problem, I've already identified that this is what I want. This is my 2 values, my M2 and my V2. My concentrated original molar stock solution is 5 molar, and I want to know how much volume of that I need to pull from it and then water it down with water to get to 500 milliliters. So what that is actually going to look like, I know I have a 5 molar solution. I'm going to take some of that 5 molar out. How much do I need to take out? What volume do I need to take out to add enough water to bring me to a total volume of 500 milliliters to make that 2 molar concentrated solution? So let's see if we can now calculate that to figure out what that mystery volume is, that V1 volume. So as we mentioned before, or as we saw on the slide before, we said that this 500 milliliters was my V2. This 2 molar was my M2. This 5 molar was my M1, and I am solving for my V1, right? So my equation is going to be M1 V1 is equal to M2 V2, right? So I can fill in my M1 value, that is 5.00 molar, I'm solving for V2, or V1, and that is going to be equal to M2, 2.00 molar, times V2, which is 500 with a decimal, which means those zeros are significant, milliliters. I'm not worried about that being in milliliters. I just know to expect that when I solve for my V1, that will be a representation of a volume in milliliters as well. Okay, so for my calculation, I'm going to multiply these two numbers together, and then I'm going to divide those two numbers by the 0.5, because mathematically, what I'm doing here is I'm getting rid of the, or not 0.5, 5 molar solution by dividing both sides by it. Today's, I feel like, a lesson in some algebra, which is, fine. We could all use an algebra lesson. So that's how I get to V1. Let's see. So we go 2 times 500 divided by 5. Okay, so I get 200. Amazing. You were like, yeah, 200. Well, 200 what? Well, y'all, I solved for a volume. Well, what are the units for? It's whatever the units for the other volume were, which are milliliters, but watch out on your sig figs. Every number in this problem has 3 sig figs. You're like, well, that's 3 numbers. Yeah, but you're not telling me those 2 zeros at the end are significant. The way that you do that is by adding a decimal. So 200 milliliters, right? So it's like, well, what the heck does that mean? I've completely forgotten. Well, let's go back to our little thing, our little visual. And we see here, oh yeah, I was trying to figure out how much of that original concentrated 5 molar stock solution I needed. And then I would water that down or add water to that 200 milliliters to get to that final volume of 500 milliliters. Okay, so super exciting. Let's do two more. We'll do 2 more problems. Okay, it says 50 milliliters of a solution are diluted to. So I have a volume being diluted to something else. So this is my V1. This is the volume of my concentrated stock solution. So that's diluted to a volume of 100 milliliters. So that's my V2 where I want to end up. The concentration of the diluted solution is 2 molar. So that's my M2. What was the concentration of the original solution going in? So kind of visualizing what we're looking at here, we know, okay, that concentrated solution, we had that volume, and we knew that we added water or diluted it until we got to a different volume of 100. And that different diluted solution with 100 milliliters was a 2 molar solution. Well, in this process, what was the molarity or the concentration of the original solution? So let's see if we can math that out. It says 50 milliliters. Oh, we already assembled all of our players here, but let's rewrite this. So that was my V1, right? Because it was diluted to this, my V2, and the concentration of that diluted solution was 2 molar. That's my M2. What was the concentration, which is molarity, M1? Okay, so my equation is M1 times V1 is equal to M2 times V2. We're using this to solve for M1, right? So I can, even if I wanted to, restate this as V1 is equal to M2 over M2 times V2 divided by M1. That's just me moving and isolating that variable to get to solve for V1. Okay, I have all of my players. I'm ready to go. My M2 we said was 2.00 molar. My V2 was 100 milliliters. And my M1, y'all see what I did wrong. I was solving for M1, right? Which means the process is the same, but I just need to get volume down here on the other side, the first volume. And a good thing is that me actually writing my units in here helps me catch those mistakes, because I would have seen myself writing a unit for volume in milliliters and being like, wait a second, that's not a molarity concentration. Okay, so that was just a little aside. See, we all make mistakes sometimes. It's not a big deal, but we can fix our mistakes, especially when we show all of the good work. Okay, so here we are right here. Yes, we are ready to math, and we will get to the molarity, or the concentration, by multiplying 2 times 100 and then dividing that by 50. So my answer is 4. You're like, great, 4 what? Well, what did we solve for? Molarity. The units for molarity are capital M, but hold up, we got to figure out what the sig figs of it all is. Everything in here has 3 sig figs. That's only 1 sig fig. To make this number be represented with 3 sig figs, you're going to do a decimal and add 2 zeros at the end. And so our original stock solution was a 4 molar concentration solution, right? So if I were to go back to my diagram showing what it is that I was looking at here, we would now have figured this out. It's like, okay, that original 50 milliliters, when I watered it down to reach 100 milliliters to make the new volume concentration of 2 molar, that original concentration, that more concentrated stock solution, was originally a 4 molar one. So now let's move on to our last example, one more example on dilutions. It says a student prepared a solution by transferring 10 milliliters of a 0.15 molar stock solution. So that is the volume and the concentration of your original stock solution to a 100 volumetric flask and filling it to the 100 milliliter mark. So that 100 milliliters is my second volume. What is the concentration of that new solution? Okay, so I took 10 milliliters of that 0.15 molar solution, filled it up to 100. Well, as a result of that, what is the new concentration of my diluted solution? Okay, so this was 100 milliliters was my V1, 0.15 molar was my M1, 100 milliliters was, or that was 10. Did I say 100? I'm not sure what I said. 10 milliliters is my V1. That's my M1. This is my V2, right? And then what is the concentration of the new solution? So I'm solving for M2. My equation is M1 times V1 is equal to M2 times V2. Now I'm solving for M2, which means I divide both sides by V2. So M2 is equal to M1 times V1 over V2. Yes? Okay, so I have everything that I need, it looks like, to plug in and solve. My M1 is 0.15 molar. My V1 is 10.00 milliliters. And my V2, we said, was 100 milliliters. Yes? Okay, so calculating that out, 0.15 times 10 divided by 100. Okay, so I get 0.015. Well, what is that? I've solved for the second concentration. That's the molarity. Okay, so my M2 is equal to 0.015. How many sig figs do we need here? That's got 3 sig figs. That's got 4 sig figs, but that only has 2 sig figs. So we actually stop right there with the 2 sig figs, and the unit is a molarity. And so here on my little picture, as a reminder, this was my original 0.15 molar stock solution. I removed from it 10 milliliters, right? And then I watered it down to create a total final volume of 100 milliliters. So that's my V2, which means my M2, my question mark molarity for my M2, we figured out was equal to 0.015 molar, which is really cool and really exciting. So that's our conversation on concentration and diluting things of different concentrations to make a solution of any desired amount of solute in a given amount of solvent.